Akawan. She's a PhD candidate, and as I just learned from her, that she will be finishing her PhD, I think, at the end of summer. And the talk is about performance perspective and in selecting best management practices for linear projects, for roadway and highway projects. And this is one of the ICT projects that also being conducted at the University of Southern University of Illinois at Edwardsville. And the second project is more about soils and aggregate, and this project is the title of the presentation is Soaked and Unsoaked CBR test results on unbound aggregates with varying amounts of fines and dust ratio. And the second presentation will be made by Goran Otmanavbi, as much as I can do. And he's a master's student, and he's also about to finish his master's, I think, soon with this project. And this is a project also partly supervised by Dr. Tutumla here at UIUC. So it's a collaborative effort between UIUC and then Edwardsville, Southern Illinois at Edwardsville. So they will not stop between the presentations. We'll finish both of the presentations, and I will receive the questions at the end of the two presentations. So I'll let Azadeh to start his presentation. Let's give her a warm round of applause.
Thank you. Hello, everyone. As Dr. Ozer mentioned, I'm Azadeh, PhD candidate at SIUE. The presentation I'm having today is for a project that we're doing with IDOT, and it's called Performance Perspective in Selecting BMPs, or Best Management Practices, for the linear projects. Well, that's just the outline I'll go through. By building more roadways and highways, and even widening them, we are actually putting more impervious surfaces, and the consequence of that is changing the natural hydrological response. It means like we will have more, since it's impervious, we will have more stormwater runoff producing by having them. So the concern with the highways, stormwater runoff is increasing because of that. And looking at 2014 data by FHWA, it shows that about more than like 78% of the roadways which are owned by DOTs, they are rural. And rural means like they are in the areas with 2,500 population, and they usually have the open drainage system, and that open drainage system and open channels can already take care of those runoffs. But the problem will be for the where we have the steep slopes, and also like the areas that we have the lower permeable soil type along the road. And so the natural system won't be that effective. So to mitigate that problem, the solution is using the BMPs, specifically bioswale and also the linear BMPs. Well, talking about the linear BMPs, EPA divided actually the BMPs into three major groups. First one is the point BMPs. They are the one that can capture actually the entrance of the runoff to it is a specific location, such as like the ponds, or you see other examples here. The second type is the area BMPs, the ones that are actually land-based management type, like the previous pavements. The third one is the linear BMPs. Linear BMPs are the narrow type, actually narrow-shaped BMPs, best management practices, and they're usually alongside the roadways, and they're adjacent to stream channels, and they increase the infiltration, and somehow they add some aesthetic value to the roadways as well. The examples are like bioswale, vegetated filter strip, and infiltration trench, that in this project we actually covered all of them, but today, because of the time, I just covered the bioswale. And as you see these pictures, they are showing different bioswales. As you see, the bioswales can be in a different width and right by the roadways. Well, their performance, based on the previous studies, they reported a range of actually runoff reduction, which is between like 50% to 94%. Well, this 50 to 94 is actually wide range, and the main reason is because each of these studies have been done in a different location, so the site characteristics and also the project characteristics is different, and that kind of affects on it. So, and for example, you see International Stormwater BMP database, like they monitor 13 biosoils, and the average they reported is like 48% runoff reduction. And also another thing is all these biosoils, like they have been studied, they are not all in the same age, they're not all like brand new one. There are also reported that 70% of them are like built in 1990s, 1980s, or even like earlier. So even age can affect on the performance of them. Well, another way of actually, other than just the field test and measuring the performance, there is another way using is the simulation softwares. There are different softwares. 4 of them I mentioned here: HSPF, SWAT, LTHIA, LID, and also the SWIM. So these are the ones that we can also use to actually evaluate the performance. Well, the main goal of this research is actually to be trying to find a performance cost matrix of the BMPs to capture 1 inch of actually rainfall on the highways. And it actually has 3 phases, as you see: simulation, also field test, and the cost calculation that I explain more, like talk about simulation and field test today. And here you can see the whole research methodology. We first needed to do the modeling approach and make a model for the like a catchment area. We defined an idealized catchment area, and also then the same time we ran some field tests. And for that field test also we modeled that, and then based on the results we got out of the field, we calibrated it, and then we used the calibrated parameters in the idealized catchment area that we defined, and then the results for that performance after we got it, we will use it for the cost actually calculation. But for the modeling, the software we picked is PC Swim. PC Swim is a luxury type software for the swim that EPA owns it. And actually, it has kind of good features. Specifically, the one that it has is the tool is called SRTC, or sensitivity-based radio tuning calibration, that you can calibrate between your field test and also the simulation part. So here you can see the idealized catchment area model that we actually defined, and we defined it based on the standards and like the typical sizing and everything for such a catchment area. And as you see, it has this is like one direction of the highway. The highway we picked has 4 lanes and 1 shoulder. Why we picked 4 lane? Because we usually the problem is in the urban area, and when you get close to urban area, you see the highways like have usually 4 lanes. And then the right of way, including the forest slope, the embankment, and the level ground, and the back slope. Here you see the plan view of the model when we do not have any BMP, so we call it pre-BMP scenario. Then when we want to add the BMP, we will add it to this level ground. And now here you can see when we have the biosoil in there, and the biosoil that we used for it is the one you can have a different bottom width for it or width for it, but the one that we picked is the typical. Usually they go with the 5 feet bottom width and the 2.5 feet depth. So this is showing the post BMP or biosoil scenario. Also, we wanted to know how what if like the soil type in the area, the natural soil type is effective as well, because if it is like more sandy and has higher infiltration rate, it will already capture some runoff before it gets to the BMP. So here we actually considered all 11 type soil, but here I'm just going to show like results for silt loam and silty clay. These are actually the parameters for each soil type. Also the vegetated surface, the cover on that area. We considered if there is no vegetation, if there is turf grass. Turf grass is the one that you usually see is typical on the side roads, and also another one, prairie grass. But here I'm just showing, I will show the result for if we have the turf grass in that area. For the field test, we actually in Southern Illinois University, in the property, we built some BMPs there. And that our work for the field test had three actually phases, like first the layout, which layout we want to go with, also which storm event we want to test with it, and also which ages of the BMP we're going to have in there. So here you can see the plan view of that. We also did some, made some infiltration trench as well, but today I'm just talking about these bioswales. Well, we built those 3 bioswales, and since we couldn't build the whole highway and everything, so we calculated, based on the layout we picked, we calculated how much volume of the runoff is going to reach the bioswale, and depending on the flow rate, that we controlled it with the flow meter and also a valve, so we put it in the tank and then we ran it for each of the bioswales. And here you can see a plan view of the bioswale. Since the water, when it gets to a bioswale, it's like a sheet flow. So to be able to make it like a sheet flow, we need to have a perforated pipe so that it makes that sheet flow. The bioswales, the sizing are 8 feet long, 3 feet wide, and also 4 feet deep. So, and we filled it with gravels, and also on top of it about 1 foot growing media for the vegetations. The plan view, there are different like scenarios we could pick. Here, the one on top, you see it's just the plan view like for the model. We assume there's going to be 50 feet width of the upstream watershed for that bioswale. And we could either go, in this 50 feet, we could either go with 1 lane or 2 lane or 3 lanes road. So we actually picked the 2 lane one, and we went with it. And for the precipitation, IEPA work groups recommended in 2013 that any new development area, they need to be able to take care of the first 1 inch rainfall runoff from the roads. So we use the IDF table, intensity, depth, frequency table, which is for Illinois, and also we picked the southwest area. And as you see in this table, the blue column shows the duration, the green one on top is the frequency of the storm, and the red one is the accumulated rainfall depth. So we wanted 1 inch, so we picked the 1 inch, but which year frequency? Usually the bioswales and BMPs are built in a way that they can capture maximum 10-year return storm. So okay, we pick here 1 inch, 10-year, then it will take about like 10 minutes, or like 5 years, it was like 12 minutes, not that a big difference. So we skipped that. 2 year, about 20 minutes, and also the 9 month we picked about like 45 minutes. So also, we looked at the closest rain gauge data to find out maybe we want to have a rainfall in a longer time, and like in the medium actually depth, or also the high depth of it. The maximum is usually like 4 inch. So that usually takes about 6 to 7 or 8 hours. So we also picked them to run some tests. Here you can see the table that shows the scenarios for the precipitation. Now aging, okay, bioswale, what changes when it ages? It's like by the time it gets older, it usually like debris, sediments are gonna accumulate on top of it, and if there's no maintenance on it, it will kind of affect on the infiltration rate, and then so the performance actually decreases. Where those sediments come from? Usually from that like forest slope. So and how could we figure it out that how much it will be? So we use that USLE equation to find out the soil loss, the amount of soil loss. I'm sure you know about that USLE equation. And then after calculating it for these scenarios that we picked, it was about 1 ton per acre per year sediments. So we assume that if there's no maintenance going to happen or to take them away, the first bioswale, as I said, we have 3 bioswales. The first one, we picked it brand new, so no sediments on it. the 2-year-old we picked, that for each year, if it is 1 ton per acre per year, it would be about 3 kilograms of the sediments accumulated on it. So for 2 years, we counted how much, and for 10 years, how much. So, and also we assume that the gradation is going to be like uniformly, so evenly spread on it. So we built our biosoils in that way. These are the test matrix, as you see. There are some bold. The bolds are the one that we for sure did the test on. But like, for example, the one which are not bold are the one that we figured out there's no need to do it. Because, for example, for the brand new one, even 10-year return storm, which happens 1 inch in 10 minutes, it could take care of all of it. Even we ran the 2-year-old, it could take a 2-year return, it could take all of it. So there was no need to do even the less amount of rainfall or even longer time for it. So, and also to find out the effectiveness of that, we calculated in 2 ways. Effectiveness of the system, the whole system, including the highway and everything that ideal is catchment area that we define based on the input, which is precipitation, and output, which is the runoff out of it, and also the BMP unit performance, which is just the BMP or biosoil. For example, the input to the biosoil is going to be precipitation and also runoff from the highway, forest slope or back slope, and then the output would be just runoff. So like simply calculation, we could get the performance for just the BMP units. Here, this graph shows the result for the simulation, the modeling before we calibrated. As you see, the y-axis is the performance runoff reduction. This is for the whole system. When we have the silt loam, this white or like hollow column is the pre-BMP. When there is no BMP, the performance was about 60%. But when we add that bioswale, it goes up to like 80-something%. Or also silty clay, the same trend. And since the silty clay also is less, actually the infiltration rate is lower, that's why in total, like comparing to silt loam, is actually lower performance. Then here are the results from the field test. Field test, as I said, the brand new one, it was capturing all of it, so it was all 100%. The 2-year-old bioswale, this darker column is the inflow, which was, for example, when we had the 1 inch, it was like about 250 gallons of water input, and the runoff, as you can see, when we had the 9 months return is the longer. It was like 45 minutes. If we had the same amount of water in longer time, it was no runoff. Actually, it could have a better performance. And also for 10-year, it's the same trend, but as you can see, like 9 months had also the runoff because it was like in a less time. And then based on that, those results, we actually calibrated the system with, depending on the uncertainty. After calibration, as you can see, the field test and the simulation one, the solid ones here are the simulated one, and the hollow ones are the field result. After calibration, you see the result, actually result got much closer. Before that, it wasn't. And also, after we calibrated it, we used those calibrated parameters in that idealized catchment area, the model, and we ran it for the brand new one, 2-year-old, and also 10-year-old one. As you see, this one shows the one when we have the silt loam. Brand new one, previously before we calibrate, it was like about 85%. After calibration is 90%. But then when it gets older, it gets 2-year-old, it decreases to like 73. And then when it gets 10-year-old, it gets up to like about 60% actually the performance. And for the silty clay, previously it was like less than 80% before the calibration, but after calibration is like about 85 or 86. And then when it gets 2-year-old, it decreases the performance to 60%. 10-year-old, it decreases to about 40%. So as you see, as it gets older, the performance decreases. So the total calculation, conclusion here is, well, when we run the model at first, it gives us the result will be for brand new bioswale. The result we get from them, it's not like older ones. And also we learned from here that the aging will actually affect on the performance. And like the brand new bioswales, if we the total result for the all 11 soil type, the performance for the brand new would be between the range between 85 to 96% reduction it will have. And also we learned that the aging of the bioswale, the deterioration is in a way that it causes the decrease in the infiltration rate because of the sediment accumulation. And when we have in the silt loam area, well, the decrease, the trend for the deterioration is from 90% in brand new one to 60% in 10-year-old bioswale. And when we have the silty clay, we have 85% in brand new one, and then when it deteriorates, it gets 10-year-old, it goes down to 40%. The reduction. So I do acknowledge IDOT and also ICT, also Scott Marlowe from IDOT for supporting this research. And thank you. I was on time? Okay, good. I spoke so fast.
We'll proceed to the second presentation.
You go ahead.
Questions to the end.
Oh, yeah.
Can do it. Hello everyone, I'm Goran Osmanauni, a graduate student from SIUE. My research is about soaking and unsoaked CBR test results on unbound aggregate, how they're different if we change index properties like fines content and dust ratio. First, we should understand what are the factors that affecting on aggregate strength. First of all, we have aggregate type. Which type of aggregate you're using? Is it limestone? Is it gravel? Is it basalt? And then are they crushed or uncrushed? How many percentage are they? So in this research, we use crushed limestone, fully crushed 100%. And aggregate gradation. Gradation contains maximum particle size, which in this research we use maximum particle size of 1 inch, and dust ratio, which is a person passing number 200 sieve over person passing of number 40 sieve. We use a variety of them in this research, and fines quantity and quality. Fines, it means person passing number 200 sieve, and what a percentage you are using in your research, and what is the quality of it? It means what is the plasticity of this? So you can find it in Atterberg limits. In previous research, we found that as higher fines content used in the base and subbase, lower strength recorded. And if lower plasticity index used, higher strength recorded. And about dust ratio, many states and specifications, they don't require like limit control for dust ratio. But some standards, like they put 0.66 as the maximum dust ratio you can use. Those are the current standards and state specifications. For example, in maximum allowable person passing number 200 sieve, some states and standards like AASHTO and Colorado, they allow up to 20%, and some states like Indiana, 12%. About PI, plasticity index limit, most of them, they're capping it at 6%, but some states like Illinois, they said PI maybe is not required if you use dust ratio of 0.6. About liquid limit, most of them capping it under 25%, and about dust ratio, as we said, they put it on 0.6 or 0.66, and some of them, they don't have limit control on them. So the importance of this research is how soaked and unsoaked CBR are different from each other. on unbound aggregate. For example, many technicians, they use soaked CBR, unsoaked CBR as equal to soaked CBR at wet side of optimum moisture content. This statement can be true for samples like that, but how about this sample? So the unsoaked CBR is way higher than the soaked CBR, even at the wet side of optimum moisture content. And another case, we have many studies that propose correlation between soaked and unsoaked, but all of them are in soils. So then what about aggregate? So those are the two factors that pushed to do this study. That's our test matrix. We use it plasticity index of 5%, 9%, and 13%, and fines content of 5 and 12, and we have dust ratio 0.4, 0.6, and 1. For example, B12 sample has a dust ratio of 0.6 and fines content of 12 and plasticity index of 5, and so on for the other samples. So each group of this group test, we have 4 to 5 samples to produce a compaction curve to find out where's optimum moisture content. And we have the same thing for soaked and unsoaked. So each group of them has it's doubled, one for soaked and one for unsoaked. So we used a gradation CA6 for base and subbase, which is one of the most used aggregate gradations for base and subbase in Illinois department, and those are the lower and upper limit for IDOT CA6, and those are the samples that we produced. Material preparation, first of all, the provided aggregate, first of all, wash it, and we kept the fine content. The coarse and the fine are going to oven for 24 hours. Then we're sieving them and screening them and making them ready to remix it for a new sample to produce those types of samples. About the dry density, this is a typical curve of dry density. So we figured out as fine content increases from 5% to 12%, their maximum dry density is increasing. That's for all the samples. And we figured out as plasticity index increased, for example, here in this case from 9% to 13%, their maximum dry density gets decreased for all the samples. So the results of soaked and unsoaked CBR, we found out the samples with 12% fines content and samples for 5% fines content, their soaked and unsoaked CBR trend are the same, but with different intervals. For example, for this one, which contains 12%, the unsoaked CBR have the same trend as the soaked CBR, but with different intervals. For the samples of 5% fine content, they're really close from each other for all of the samples. And to make our data more practical, for example, at the field, you target 6% optimum moisture content, but you don't get it always. Sometimes you get 5, sometimes you get 7. So what we did is we made an average value of optimum moisture content and optimum moisture content plus 1.5 and another one with minus 1.5 to represent exactly this zone to make our data more practical. So for samples with 5% passing fines content, so we figured out as dust ratio increased from, for samples with 0.4 dust ratio, 0.4 dust ratio, increasing PI and soaking doesn't affect on the samples. As you see here, the sample A5, which is PI of 5 and dust ratio of 0.4, the soaked and unsoaked values are 60%, but then here with PI of 9, it also gives the same. So that means for samples with dust ratio 0.4, PI and soaking doesn't have any effect on it. So we found that based on our test result, samples with 9% PI and dust ratio of 1 showed the lowest soaked and unsoaked CBR. So those bold lines are soaked and those hollows are showing unsoaked. So among all of the samples with 5% fine content, sample F5 shows the lowest strength. And about rising PI from 5% to 9% for samples with dust ratio 1, which is samples C5 and F5, we figured out as plasticity index increasing, their soaked and unsoaked CBR are getting lower and lower. About samples with dust ratio 0.6 and dust ratio of 1, which means take out sample A and D with it, which they have dust ratio 0.4, the difference between soaked and unsoaked CBR are below 20% for all of the other samples. Take out dust ratio 0.4, the others are below 20%. So for samples with 12% fine content, we figured out the lowest value targeted when samples with dust ratio 0.4 engineered. So for among all of them, you can see the lowest value of unsoaked and soaked CBR are for samples with dust ratio 0.4, which is group A12 and D12. And comparing both samples with 5% and 12%, we figured out that as fines content increases, the strength of samples with dust ratio 0.4 are getting lower. So if we compare A5 and A12, which they have the same index property values other than fine content, which this one has 5, this one has 12, their strength, soaked and unsoaked, is getting decreased. For the samples with dust ratio 0.6 and 1, when we increase the percent passing from 5 to 12, the unsoaked values are getting increased and the soaked values are getting decreased. Why? Because when you have unsoaked CBR, the more fine content gives more strength to your sample. But when you soak the sample, the fines content are getting wet, totally soaked, then it gives a slip medium that the aggregates are slipping on top of each other. So in this way, your strength is getting lower. By using all of this soaked and unsoaked data, we made a prediction by using statistical method. So you can predict a soaked CBR from available unsoaked CBR test with using some factors. Those factors are plasticity index factor and fines content factor and dust ratio factor. So those factor values are presented in this table. For example, if you have a 5% plasticity index, you use sigma p as 0.79 and so on for the others. And for example, if you have a sample with dust ratio 0.6, you use 0.97 as your factor. So this figure shows a measured soaked CBR with an estimated soaked CBR. So that's the agreement line. If you can see, we have two to three sample outliering. The other samples are showing in a good agreement with the soaked and unsoaked CBR. So this model gives about 90% error range, which we can say it's a good error range for aggregate. So then we said, let's validate our model. Maybe we can, it's not working for the other samples. So we prepared some samples with this index properties, dust ratio 0.4, PI5, and fines content of 8%, which is not used in this study. So we figured out the model is working for those samples which has index properties lay between the maximum and minimum that use it in this study. So 8% is light between 12% and 5% that we use in this study. So as a conclusion, we figured out that samples with dust ratio 0.4, soaking is not affecting on it, and also plasticity index is not affecting on it. So CBR tests show that plasticity index on both average soaked and unsoaked CBR for samples with dust ratio of 0.4 and 0.6 are minimal, which is almost not affecting on it. For samples with DR value of 0.6 and 1, as we increase the fine content, resulted in decreasing soaked CBR and increasing unsoaked CBR. And finally, a prediction model was developed to estimate soaked CBR from available unsoaked CBR by using some factors that presented earlier. Thank you.
All right. For both Azadeh and Goran.
Yes.
So at the beginning, you said your objective was to come up with like a cost matrix, right, for the bioswales? So how did you quantify the cost, or how did you compare?
The cost, it has its own model. I myself didn't work on it, but there is another of our faculty working on that, and but it has a specific algorithm based on what specific things they need, the area and everything, and then it's like based on, actually the way they're calculating is like, for example, as if you remember, I showed you like the percentage reduction, like different soil type, or also we also have for different like vegetation cover. So, and also there is another factor of the width of that biosoil. Like for example, the one I showed you had like 5 feet bottom width, but we also went forward with like up to even like 10 or even 15. So depend on the width of it and how much cost does it need to build. That algorithm was used to show that how much does it cost, which one makes like is more beneficial to build. If you want to build like a double size as what I showed you here, and it's gonna cost a lot for them, but the percentage reduction is not gonna make that difference. So why to pay that much? So it's actually a different algorithm.
So you're basically trying to find which design is the most effective for the cost?
Yeah.
Okay.
Yeah.
And the reduction volume percentage runoff, you want that to be high, right?
Pardon me?
You want that number to be high?
More than 80%, it makes sense. And usually, as I showed you, like specifically for the brand new one, it had from 85% to 90-something%. And well, it's good, but even we tried it if we built it with a smaller bottom width, like up to 3 feet. How does it work? And well, based on that, the whole cost is like, for example, also the final cost is, as I shown you, it's just a bioswale, but there is also infiltration change, vegetative filter seal, vegetative. Might cost more or less, and also like infiltration trench, it's just filled with gravel, and the maintenance for it is so high, and so it doesn't make sense after the cost calculation to build that, even if they just build the bioswale, you know, or even vegetative filter sieve with the lower cost for the maintenance will work for them. So
Gotcha.
yeah.
Questions?
One question for you, Goran. So you showed in your results,
In your abstract, you were mentioning that the highest plasticity and also lowest CBR value, but in your results, when you have your plasticity at 13%, it looks like it's almost performing similar to.
So
Yeah.
13% is totally outlier of our,
Outlier, okay.
yeah. But I mean, we get sometimes like results like that. We don't know what to do with it, and sometimes like here, their socket is getting increased, but then socket is getting decreased, and so the effect is random when you get past 9% plasticity index. Sometimes it gets up, sometimes it gets down.
Have you done other types of tests in addition to CBR?
So that's part of the project. We are doing a triaxial test on them, and we are doing resilient models of them. So we figured out CBR is not a good test to show a difference in plasticity. So we're starting to do, actually we're doing resilient modulus tests to see how they're different in plasticity. What is the effect of that?
Did you consider doing permanent deformation?
Yes.
Okay.
But that's actually a part of the project. It's not a total part.
Okay. That's it. Sam, are you okay? Huh? You good? Because since Professor Tutundar is not here, I just want to make sure that they're okay. Okay. Any other questions? I think excellent. 2 presentations. Thank you so much for coming all the way. They are driving, by the way, 3 hours, right?
Yeah.
They came all the way 3 hours from Mansfield, so I really want to thank you both of you
Thank
to
you
come
so
over
much for
here to
having
do the
us.
presentation. Yes.
Thank
Let's give
you.
them a warm